Welcome back, everybody. We're now into our third section on confidence intervals. This one we're going to talk about today is confidence intervals for population variance and standard deviation. All right, it's going to be a fairly similar process to the other two sections. And in the first section, I talked about the motivation for confidence intervals. So if you want to review that, go back to the 8.1 video. Right now, I'm just going to get into the nuts and bolts of what we need. So let's just review a little bit. All right, our population variance is denoted by our sigma squared. Our S squared is our sample variance. Our N is our sample size. If you'll remember, N, when we're doing probability, could have been number of trials. In this case, we're going to talk about it in relation to sample size. Our S is our sample standard deviation. Remember, to get from variance to standard deviation, you're just doing the square root. And our sigma is our population standard deviation. We have not used some of these in a little while, so it's always worth it to go back and talk about it. Now, the difference between getting a confidence interval for the mean and getting one for the variance and standard deviation is we're just going to use a different distribution. The distribution that we're going to use is called the chi-square. Square distribution. All right, and a chi is a Greek letter. It's made, kind of give a fancy part of that x and a straight one there. I'll make good and bad x's, and you square it like that. All right, and the chi-square is calculated by n minus 1 times s squared over our population variance. When we graph our chi-square, initially it looks fairly normal. However, there are a couple of differences. I'm going to just sketch a graph right here. All right. It is somewhat bell-shaped, but it's not symmetric. And notice, right, it starts at 0. So I'm going to list these. Okay, so bell-shaped, not symmetric, starts at 0, so no negative values. All right, and we're also going to continue to use our degrees of freedom. I talked about what degrees of freedom were in the last video. If you want a refresher, go back to that. Now, the key difference here is our chi-square is going to give us area to the right. In our other two distributions and tables, we always got area to the left, and then we had to do 1 minus to get area to the right. The chi-square is going to give us area to the right, which is a very key difference and one that you definitely need to keep in mind. All right, so at this point, let's star this. At this point, I just want to jump in and learn how to get some of the chi-square values. All right, so here is our first example. So example, n equals 12, and I want the 95% confidence interval. All right, and I want to find these critical values. All right, so remember, we always had our alpha and our alpha divided by 2. So to get alpha, we do 1 minus 0.95, which equals 0.05, which equals alpha. And then if we divide by 2, I get alpha divided by 2 equals 0.025. Now that 0.025 can be found here. So that's actually a better chi-square than the last one I drew. There we go. All right, so what I want to know is I want to know what those two values are. All right, so we need to start by getting our degrees of freedom. So our degrees of freedom are calculated the exact same way. Degrees of freedom equals n minus 1, which in this case would be 11, because I said my sample size was 12. All right, so I'm going to go down the left side of my chart to 11 degrees of freedom. And because I'm getting area to the right, so if I'm going to get this value, this area to the right is 0.025. So I'm going to go down to 11 to 0.025. And then I get my value, which would be 21.92. Different charts go out a different amount of decimal places. So go out as many decimal places as your chart will allow. Now to get this one right here, we need, again, area to the right. So this is 0.95. I'm going to add that to my 0.025 to get an area of 0.975, and degrees of freedom were 11 once again. And to get my other value, I look on my chart and I see 3.816. All right, so that's how I got my two values. And again, the chart is made for you. Use it. It is an estimate. So like I said, different charts go out a different amount of decimal places. So it is an estimate. All right, so now let's figure out how to estimate the population variance. All right, so it's going to start out very simple. I'm going to use the same exact information we used in our example. So this starts out very similar to our way to calculate our chi-square. Where did that go? I think it's up a little bit. Right over here. However, I do not have my population variance. That's what I'm looking for. So instead of putting population variance in our denominator, we are going to place our chi-square right value in this denominator. And our chi-square left value in the other denominator. Now you might say this looks a little strange because on the left side of my equation, I'm doing the chi-square right value. So let's think about it for a second. It's not necessarily a proof. It is just a little bit of logic behind it. The left side of my inequality, I want to be a smaller number. correct? So I want the low number to be here, right? And I want the high number to be here. If I put this value into this denominator, I'm going to get a smaller number than putting this value in this denominator, which will make a higher number. All right, so a little bit of logic to it. It is something to keep in mind. It is one way that people make mistakes. So your chi-square right goes there, your chi-squared left goes in the other spot. All right, and if we wanted to get our population standard deviation, we would simply do the same exact formula, just under a square root. All right. So let's go to another example. I'll make one very straightforward. We are going to find let's just find our chi-square numbers, our right and our left. So find chi-square right and chi-square left values for n equals 25 at 90% confidence. All right, so this is our fairly typical, very first straightforward problem. Why don't you pause the video, think about it, and we'll talk about it on the back end. All right, so hopefully you had some time to think about it and maybe think about what you might do. I'm going to talk about what I would do. Now, for me, the first thing I'm going to identify is that I have degrees of freedom of 24. I always like to put things down that I know right away. All right, and the next thing I'm going to do is I'm going to draw a picture because I know how to do that. All right, so again, I'm going to just kind of estimate my chi-square. I'm going to put in my 0.9 right there. And I'm going to put in my alpha divided by 2. My alpha is going to be 0.1. And my alpha divided by 0.05 in each tail. I'm just taking that 0.1 and dividing it by 2. Now remember, for our chi-square left and our chi-square right, I'm actually getting better with those chi's. We need to use our area to the right. So to get our right value, right, my area to the right is going to be, my area equals 0.05. And again, my degrees of freedom are 24. So, and when I look on my chart, I get a right value of 36.415. Again, like I said, different charts go out different decimal places. So if yours goes out more decimal places, you should put more. For my left value, again, I'm using the area to the right. So I've got 0.05 plus 0.9, which gives me an area of 0.95. And again, my degrees of freedom are going to be 24. And I get a value of 13.848. This is very key in order to be successful with your chi-square. The first thing you need to do is be able to find those values. All right. All right, so let's go to and now an applied example. All right, so let's try this example. Find the 95% confidence interval for the variance and standard deviation of the nicotine content of cigarettes manufactured if a sample of 20 cigarettes has a standard deviation of 1.6 milligrams. All right, this is a fairly common example and a fairly good use of this confidence interval because while cigarettes are manufactured in a fairly uniform fashion, machines do not do everything as exact as we would like necessarily. So every once in a while, cigarettes are tested for their nicotine content. And too much nicotine content could be harmful. All right, too little, and you could have a weak cigarette. So let's start by finding our chi-square values. All right, so I'm going to scroll that up a little bit. So if we have a 95% confidence interval, I could have drawn that better. That's okay. There's my left and right values, 0.95. All right, my chi left value and my chi right value. All right, so for my right value, I have an area of 0.025. Right, because that's what's left in both of our tails. And for my chi left value, I have an area of, actually that's a terrible 0.975. My degrees of freedom for both equal 19. All right, so at this point, pause the video, look up the values on your chart, and we'll talk about more on the back end. All right, hopefully you looked up those values on your chart. For my chi-square right value, and these should have had squares on them. My chi-square right value, I got 32.852. For my chi-square left value, I got 8.907. All right, so now we have everything you need in this particular problem is here, right here in the problem, except for the chi-square values. All right, so now that we have our chi-square values, let's just fill in our confidence interval. So my confidence interval, again, let's do the formula. It's n minus 1 times our s squared over our chi-square right less than sigma squared n minus 1 s squared chi-square left value. Let's just now, why don't you pause the video? Here, I'll scroll up a little bit, and let's fill in some of those numbers, and we'll talk more on the back end. All right, hopefully you got the numbers from the problem once again. So I'm just going to start filling them in. It's 20 minus 1, 1.6 squared, over 32.852. So then 20 minus 1, 1.6 squared over 8.907. And if you didn't, let's do the calculation now, and I'll be right back with you. All right, so when I did the calculation, I got 1.5, which is less than sigma squared, which is less than 5.5. And that's our confidence interval for the variance. And now we need our confidence interval for the standard deviation because the problem asks for it. To get our standard deviation, we simply need to do our square root. So I got 1.2 and 2.3. All right, hopefully you got the same thing. I always like to finish mine off with a sentence. So my sentence could read something like this to tie it back into the context of the problem. One can be 95% confident that the true standard deviation for the nicotine content is between 1.2 and 2.3 milligrams based on a sample of 20 cigarettes. All right, if you wanted to do the sentence for the variance, you could, but it's much more common to talk about standard deviation than variance. As you noticed in this, we've used standard deviation quite a bit more. All right, there's a lot more practice to do, but I hope this gets you started. Thanks for listening.